Welcome to our talk. We're going to present new attacks on cryptocurrency wallets. That is a joint presentation with Omer Shlomovits, who discovered most of the attacks that we're going to present today. So we both have experience with enterprise wallets, and we're both interested by auditing the security of threshold crypto and MPC product. So let's start with the basic notions. We only have so much time. So first of all, what is a wallet? So a wallet is the way to protect your digital assets, your cryptocurrency, anything that runs on a blockchain. So as you may know, you do not literally store Bitcoins as a piece of data. Instead, you store the private keys that you will use to issue a transaction. So if you lose access to this private key, you lose access to your money. And if someone steals your private key, then they can spend your money. So you want to protect this private key. There are different types of wallets. You might be familiar with mobile wallets that run on mobile phones, on online wallets, which are essentially web applications, on the hardware wallets, such as Ledger or Trezor devices, which provide you quite higher security, and with paper wallets when you print out your key and you put it in a safe somewhere. So enterprise wallets, and specifically wallets used by banks and financial institutions, they have slightly different needs that we describe on this slide. Maybe the biggest one is the security and privacy requirement. Because if you're a bank and you store hundreds of millions worth of data and you're regulated by some regulatory body in your country and you're audited by auditors and you have to protect the privacy of your customers, this makes things slightly more complicated and slightly more interesting. So one of the things you have to do is distribute trust. So for example, in Switzerland, there's a regulation called 4i control, which means that when you do certain type of transaction, you need at least 2 or 3 people to participate to give their approval. So in the context of cryptocurrency, it means that you need different parties with different credentials, different access rights to authorize a transaction. And more generally, you want to distribute trust between different software, hardware components in order to avoid a single point of failure. So one common way to do it, if you're familiar with Bitcoin, Ethereum, is multi-signatures, but it's sometimes complicated because it will require multiple keys. Sometimes you need a single key, and it works differently for different blockchain platforms. So ideally, you want to have something that will work on for different blockchains, Bitcoin, Ether, and all the others. So what we're going to present today is about MPC and TSS, which are techniques to distribute trust, not using hardware, not using procedures, but using fundamentally cryptographic techniques, which is one of different approaches. So what is MPC, multi-party computation? So from a very general perspective, it's a protocol, a system whereby you will receive the inputs, but in a way that is kind of encrypted in such a way you don't really know the input values. However, you will be able to compute the output, the result of some function. So in this example, we receive the encrypted version of x and of y, and we compute the result x plus y for the addition. Maybe you can guess how to adapt this for the context of wallet applications. So one way to use MPC for enterprise wallets is to split the key in different shares and different values, such that no single share of the key will give you the full key value. And the MPC protocol will receive the encrypted key share with different key shares, and will receive a kind of encrypted form of the transaction, and it will compute the signature without seeing the key. So it's not about decrypting the values and combining them and computing the result. It's really about computing the result directly from the encrypted values without ever decrypting them, so to speak. So now the question is, how do you adapt MPC? How you do something that is really optimized for the system for the case when you want to split the secret between, let's say, n participants, but you only want to authorize a subset of this participant to issue a signature. So that's what threshold signatures, or TSS, is about. And you can see it as a special type of multi-party computation. So here we usually use the notations T and N, whereby N is the number of potential signers, and T is the minimal number of signers you need to issue a transaction. So in this example, we have 3 individuals, and one is potentially malicious, where at least they look not really trustworthy. So we don't want to authorize one single person to issue a transaction. So we have a system whereby we need two parties to cooperate together to issue a transaction. And here you can see that the two persons with the shares, share 2 and share 3 in blue, can work together to sign a message without the approval of the pink guy on the left hand. So from a more abstract perspective, in TSS, you will have, for example, these two signers. Each of these two signers, they will have a different share of the key, which means that will not have access to the full key. They will receive the message to be signed, and they will run a protocol. They will follow a list of operations to work together and compute a valid signature. Now, you might ask, okay, but how do you generate these key shares? How do you distribute them? So the naive approach is to do a kind of ceremony whereby a centralized operator will generate the private key and will split this key in different shares and distribute the key to the signers. But you can actually do a more decentralized, more distributed way to split the key. It's called distributed key generation, often abbreviated DKG. So here the participants will work together, will follow a cryptographic protocol to obtain shares of a private key, but in such a way that the private key, the master key, so to speak, is never exposed to anyone. So it's quite convenient because it really minimizes the exposure of the key. So you don't have to trust a single point. You don't have to erase the key securely because the key is nowhere. It kind of sounds like magic, but that's what advanced crypto is about most of the time. So MPC and TSS is not just something that people write research papers about. It's something actually used in real systems, in real cryptocurrency exchanges. And a typical use case is cold storage systems where you have sometimes a single key, a single account that stores really tons of money, typically tens or hundreds of millions. So in this case, you want to make sure that the access to these funds, the access to the key, is distributed among multiple parties, locations, infrastructure. In case there's an earthquake, a fire somewhere, you want to make sure that you will always recover your funds, and you want to avoid trusting only one or two people with your money. And you can combine this with different technology, with smart cards, HSM, cloud HSMs, even mobile phones, to have different types of platforms. Now, what about the crypto used under the hood? What do we need to build TSS? So to build trusted signatures, of course, you must have signatures somewhere. So in the blockchain space, there are two main types of signatures being used. So ECDSA, the ticker DSA, which is used in Bitcoin and Ethereum. And now you find ED-DSA and ED25519, which are signature based on the Schnorr signing paradigm, which is slightly different and has the benefit of not using a nonce, not using a unique number per signature, which avoids some classes of attacks. And it also makes aggregation of keys and signatures easier, which is quite convenient when you do social signatures. Another type of signature that we can cite is the BLS signature, which work very differently, which are quite complicated because they use cryptographic pairings, but they make the aggregation of different keys into a master key and the aggregation of different signatures into one single signature much easier than classical signatures. So you may have heard about fully homomorphic encryption. So here we don't do fully homomorphic, we are only interested in homomorphic encryption with respect to one single operation. So the first line really defines what homomorphic encryption is about. You combine two ciphertexts, the encryption of M1 and M2, and when you decrypt the result, you get a value that is the combination of M1 and M2. So you see that we use different signs, different operands on the left hand and right hand of the equation, because sometimes it's not the same operation. So if you consider textbook RSA, which is quite insecure, but which happens to be homomorphic with respect to the multiplication, then you multiply two ciphertexts, and what you obtain is a valid ciphertext of the product of the two plaintexts. But in pi-based encryption, it's slightly different because you have multiplication on the one hand and addition on the other hand, which is very interesting features in many cases. So homomorphic encryption is also used in e-voting to combine ballots of voters, and it's also used in some TSS constructions. Commitments, which is a notion that is probably familiar to many of you. So I don't know if you're on Twitter, but sometimes you will see people mysteriously posting hash values, and they will suggest that it's because they have found some 0 day, but they don't want to disclose the 0 day, so they post a hash so that later on they can show you the start the hash to demonstrate that they found the 0 day themselves. So it's a kind of commitment. In the context of crypto, commitment is a slightly more involved technique with more formal definitions and security properties, but ultimately it's the same. So initially the setup is about the rules of the game, which function you're going to use. The commit phase is when you commit to some value X here, and you also use some value R to randomize the process. And the opening phase, the reveal phase, is when you reveal these two values, thereby allowing the verifier to check that the value that you committed to C matches the X and R that you just published. So this one is not going to surprise you. We're talking about threshold signatures. And of course, we use somewhere threshold secret sharing, and specifically Shamir scheme, which is maybe the most common and the most known construction, which relies on polynomial interpolation. So here, maybe as a reminder, you have a secret, you have a string, and from this secret, you're going to generate a list of, for example, 5 different values. And in such a way that, for example, you need 3 of these values to reconstruct the secret, but such that 1 or 2 values will not leak any information on the secret value. One variant that is often used in TSS construction is verifiable secret sharing. So it's a small variant where the owners of the shares can verify when they reconstruct the secret that the correct secret has been reconstructed, and in particular that the other participants have used a valid share of the secret and not any random value. So a common VSS scheme is by Feldman, and it was designed, I think, in the late 80s, and it's actually based on homomorphic encryption. So last but not least, zero-knowledge proofs, and more generally zero-knowledge protocols. So you might be familiar with the intuition of a zero-knowledge proof. It's a proof that leaves no information on the stuff that you're proving. It's, for example, used in privacy-oriented protocols such as Zcash or Monero. In this case, you want to hide the money being transferred, the address of the sender and recipient, yet in such a way that participants can verify that this money has been sent somewhere and that everything is correct and sound. So generally, a zero-knowledge proof is about proving a mathematical statement, such as the result of an equation, without leaking literally any bit of information, yet in such a way that the prover cannot cheat, but that they can prove any correct value to be correct, and that any incorrect value cannot convince a verifier that is correct. In the context of blockchain, you will often encounter NIZK, non-interactive zero-knowledge proof, which is just a blob of data. Instead of being a protocol with multiple rounds, you will just send one piece of data, which will be your proof. So you don't have to run multiple round trips, you just have to send one piece of data. Okay, so now based on this preliminary, I will let Omer present the attacks on MPC and TSS constructions.
I would like to start with describing the general setup in which our attacks takes place. Starting from the left, we have a user communicating with an exchange. The user and the exchange run a two-party key generation, resulting with the user getting a secret key share SK1 and the exchange getting a secret key share SK2. The user deposits funds to his address and from that point can initiate orders. Each order comes with a signature generated by running a two-party signing between the user and the exchange. On the other side, the crypto exchange runs an infrastructure to manage access to its liquidity. As part of this setup, there are several sites that together can authorize the transfer of large amounts per the requirements of the exchange. We are using here hot wallet and cold wallet to express the frequency of the use and mention it since this is the terminology used in the industry, but it is not much relevant to our attacks. Therefore, we are actually looking at two subsystems. The hot subsystem on the left is usually based on two-party protocols where we need to protect from a failure of one of the parties. The cold subsystem on the right is spreading security to multiple sites. The number of sites or parties can vary, as well as the robustness. The guaranteed security for this setup using TSS is that even if a single key holder is compromised, the attacker gains no advantage. In our attacks, we demonstrate how an attacker with full control over only a single party can break the security of the TSS. For simplicity, we assume that the exchange is compromised, modeling either an outside attacker or some insider threat. We can describe our attacks in the context of the hot and cold subsystems. In this talk, we'll describe 3 attacks. The first one works in the multi-party setting. It will result in private key deletion, which means the exchange funds will be permanently locked. The second attack, named Lather rinse repeat, works best for the 2-party setting. It allows the exchange to extract the key of the user and steal its funds. The last attack, Golden Shoe, fits well in both settings and works by sending a well-engineered message which gets all counterparties to send the attacker their secrets. We conducted a responsible disclosure on all 3 attacks. The first attack was found in an open source library of one of the biggest crypto exchanges. However, it was found around a week after the library became public, so we assume no one was using it. The second vulnerability was found in an open source code by a big MPC company. We were told that the code used in their product is different, and therefore no one was actually affected. The last attack was again found in an open source library of a big crypto exchange. You can check out the CVE for details. Before diving into the concrete attacks, we want to give another high-level analysis of the root cause for the attacks. Here, the rows describe different characteristics common to most threshold cryptography, or TSS-based protocols. At first, TSS protocols are interactive. They progress in rounds of communication between the parties. While in modern cryptography, we usually get a single party to generate a key and sign locally, here we must have interaction. This is essentially all that was needed to mount the first attack. TSS often makes use in some cryptographic primitives which are not common and not used by many. This makes them hard to understand or to nail properly how they work. Finally, it is important to note that in the real world, where an attacker can attack any one of the participating parties, a party cannot assume anything about the correctness of the messages it receives. This means that for any message sent, the sender needs to attach a proof that the message was computed according to the protocol. One common way of doing it is using zero-knowledge proofs, some of which are tailored to prove statements on particular messages in the protocol. The first attack, as we mentioned before, works best for the cold setting. In fact, we want to focus on a protocol for key rotation. This is a common industry practice. If every safe holds a secret share SK, we want a protocol for all safes to change their secret key shares, but still maintain access to the funds locked under the joint public key. Putting it simply, we want to move from the red set of secret keys at time t to the blue set of secret key shares in time t prime. This is a basic requirement for such a system because otherwise a single attacker would be able to systematically compromise site by site until uncovering the full private key. We call this attack forget and forgive since parties are forced to forget the keys, ending up in a situation where the actual distributed key is lost. Now let's move on to describe the low-level details. A Morty in our scheme is an honest party. We use a setup with 3 parties, A, B, and C. Instead of secret key share SK, let's say that each Morty holds some personal number, XA, XB, and XC. We have invariant, which is the sum of XA, XB, and XC, here equal to Y. Our task is to replace, or in other words, refresh, each of XA, XB, XC with a new XA prime, XB prime, XC prime, while keeping the invariant of on the sum of X primes to be equal to Y. For that, we use a cryptographic primitive we mentioned before called VSS, which stands for verifiable secret sharing. We let each Morty distribute secret shares such that their additive value is equal to 0. In the figure, we are only demonstrating it for the multi holding XC. This multi will generate RCA and RCB sum to 0, such that when we sum all secret chairs, their contribution will cancel out in the total sum. Each multi will collect all the secret chairs he received and will add them to his secret Xi. As can be seen, while XA prime and XB prime have changed, summing now all X primes, we get that Y prime is equal to Y as required. So are we done yet? Not exactly. We still need to delete the old secret chairs. Now this is where it gets interesting. Deleting is a step that cannot be reversed. We ask, how does a multi knows that it is safe to delete the old secret chair? The answer should be that each multi needs to make sure all other multis also think it is safe to delete. So in fact, we have an extra round of communication that is hidden here. In the system that we attacked, this step was missing. Let's see the attack. We start the same as before with establishing the secret chairs XA, XB, XC. However, now a malicious party, represented here by Convilius Daniel on top, taking over the multi that holds XC, and can send different messages to different parties. In the figure, the left side multi gets a correct message and therefore deletes his old chair. However, the multi on the right gets a corrupted message and decides to abort the protocol, keeping his old key share. While not visible in the figure, it is important to say that a multi-detection of a corrupted message is enabled due to the check done as part of the VSS primitive. As a result, the invariant is now broken. Y prime is no longer equal to Y, and the key is effectively deleted. The outcome in practice is that by trying to refresh the private key shares, we end up with a situation where it is impossible to recover the private key or to put it into any use, such as to sign transactions spending the amount locked under the original private key. A smart attacker can leverage this situation to mount a ransom attack, attacking enough parties such that all honest parties cannot reach the required threshold to execute a signature without the involvement of the attacker. For example, the attacker can require half the locked amount to publish its secret key. So we now move on to describe the next attack. We are now focusing on the hot wallet scheme, with the exchange and the user both hold secret shares of a private key used to sign transactions on the blockchain. In this example, the exchange relays the signed transactions to the blockchain. Here again, it is important for the parties to refresh their secret shares every once in a while. It could be after every transaction, for example. Conceptually, this is the same as what we saw before. Concretely, though, we are looking at a different protocol. Earlier, we assumed that the key material needed to be refreshed is a single random number. But sometimes there are some extra artifacts that must be refreshed as well. This is the case with this attack. Let's look at the concrete details. So here, Morty on the right and Rick on the left are two parties playing the exchange and the user in an honest execution. We start with the two-party key generation. We treat the protocol as black box, as the specific details are not relevant to the attack. What is important to note is that as part of the output, we introduce another crypto system, marked here in green, which is homomorphic crypto system. In particular, Rick generates a private key, and Morty learns the corresponding public key, together with the ciphertext C. This ciphertext is an encryption of Rick's secret X1. For completeness, let's imagine how a two-party signing protocol would look like. Again, treating the protocol itself as a black box. Morty inputs a message to be signed M, and both input their outputs from the key generation. As a result, both get a signature. However, we want to focus on the refresh protocol. As can be seen, if we want to fully refresh, we need to also refresh the homomorphic crypto system parts. Otherwise, the signing protocol will simply not work. Or another option is that an attacker will be able to attack one party after the other, breaking the cryptographic guarantees of the rotation. Double-clicking on the refresh protocol, we see that as part of generating the new state, Rick must prove to Morty that the encryption was done in a proper manner. That is, Proving C prime is an encryption of x1 prime without revealing x1 prime or the decryption key dk prime. The problem is this zero-knowledge proof is highly expensive. In the code we examined, a shortcut was suggested. The idea is really cool and is using the homomorphic properties of the encryption scheme. In short, instead of proving C new, C prime structure from scratch, we can just prove a relation between C new and C old. Unfortunately, they use the wrong proof. What they achieve is that the attacker can now convince the other party really efficiently that the ciphertext is an encryption of anything. So this is how the exploit works at a high level. We require Morty to allow us to call two-party rotation and two-party signing multiple times. Each time, we will change the encrypted value and try to obtain a signature. We get some information from each such query, hopefully 1 bit, until eventually we are able to extract large parts of the private key. To summarize this attack, we started with a system that distributes the signing between the user and the exchange. When we allow to rotate the private keys, the exchange hijacks the user's secret key, which means it now can sign transactions without the user involvement at all. Effectively, an attacker that attacks the exchange will be able to extract all the keys of all the users given enough time, breaking the distributed trust guaranteed from the cryptography. We named this attack Lather, Rinse, Repeat, since to mount it, we require to run 2 protocols, therefore lather and rinse, and repeat them many times. We now move on to describe the last attack. If you recall, this attack works in multiple scenarios. However, we chose to demonstrate it in the specific case of 4 parties running TSS among themselves whenever one of the parties needs to sign a message and send it to the blockchain. To explain the attack, we recall that in our kind of real-life protocols, it is required that every participant must prove it ran each computation according to the protocol. In the first attack, this was part of the VSS, where each party sent a proof together with a random value. In the second attack, it was the zero-knowledge proof. In the current attack we described, a step like this was missing. It is not all the time that a concrete vulnerability can be derived directly from a missing zero-knowledge proof. But here we show one such example. Let's look at the details. So here, Rick's play honest parties. There is first a setup phase. This happens during the distributed key generation. Each party generates parameters n, h1, and h2 and share them with the other parties. In the figure, we show it only for the Rick on top. These parameters will later be used by the receiver to generate some proofs in the distributed signing. During signing, each party takes the n, h1, and h2 received from each counterparty, probably now saved in memory, and sends some proofs using these parameters. In the figure, we use f31 to abstract the exact data sent from the left Rick to the Rick on top. What is important to our attack is that this is a function that depends on n, h1, and h2. Therefore, the attack goes in 2 steps. At first, during key generation, at the beginning of time, the attacker sends n, h1, and h2 to the rest of the parties. They can be anything because there is no check in the implementation. The second step is to receive proofs from all the parties during a single threshold signature. From each such proof, the attacker will extract the secret key share. To summarize this attack, we start with a key distributed between the different parties. After the attack, all key shares will be copied into a single location, which means that the attacker will be able to sign transactions, ignoring all other parties. We derived the name for this attack because a simple one-time message at game time lets one party win it all. Next up is JP with some recommendations.
So to conclude, we would like to share some general advice to help you avoid the kind of security problem that Omer just described. So first of all, minimize complexity. So it's quite commonplace in security, and it's of course easier said than done, but it's still important as it's the source of a lot of headaches and wasted time, at least from my perspective as a security auditor. So a lot of this crypto is by definition quite complex, as you've seen. But you can still minimize sometimes the complexity by avoiding implementing useless stuff. For example, only implementing what you need, and also by avoiding useless levels of abstraction, by not introducing new terminology or new notation. For example, by using the same symbols as in the paper, it makes things a lot easier. So the second point here is about languages, about coding. So I completely agree with Moxie's point where he says that code should be optimized for readability instead of writability. So what it means is that instead of aiming to have like the most elegant or the most concise code, you want to prioritize code clarity, as it will make it much easier for the auditors, for anyone to understand what your code is doing, and also to find bugs therein. So be it purely logical bugs or bugs specific to the language being used. This part is about a class of bugs that we found and which are related to the understanding of the academic paper. Sometimes the academic paper that you implement is very correct in terms of academic correctness, but nonetheless ends up in something completely unsafe. So how can it happen? So there are three main classes of problems here. The first one is the fact that the papers, they will usually not describe how you encode data, how you parse the serialized data, and that's also where a lot of security problems happen. Also, some papers describe a protocol in terms of generic security level, but without giving you a concrete instance, without giving you concrete parameters. And it's your role to find the good parameters, the choice of primitives, for example, which elliptic curve to use, which hash function to use, which key size to use. So you want to make sure that you pick parameters that end up in a scheme that is secure enough. For example, if you aim for 128-bit security level, you want to make sure that all your components will guarantee this security level. And the third bullet here, incomplete or confusing definition, is illustrated by this example of a zero-knowledge proof of factorization, whereby a prover proves to a verifier that they know the factorization of some RSA models. So, which means without leaking the factors. The problem here is, as you can see in the small screen cap, there's a common input, capital N. The problem is that the authors of the paper had one understanding of common input, but they did not describe it in the paper. So what they understood is that common input was a value magically given to both the prover and verifier beforehand and not controlled by the prover. However, the implementer, they understood that common input was just a random value, potentially chosen by the prover. And the problem is that if you do it this way, it becomes completely insecure and completely broken because anyone can forge a proof. So that's a very good example of something that is safe on paper and completely insecure in practice. So to conclude this part, maybe a disclaimer: we don't mean to recommend against MPC and TSS. These are really great technologies that can sometimes provide you with much higher security level, but at the same time, they're also relatively recent in terms of real-world applications, and we're still learning a lot about how to improve their security in terms of procedures and in terms of code safety. So if you have questions about this talk, feel free to contact us directly. You will also find more details in the paper, and I would like to thank you for following this talk in this unusual setting. Thank you very much. Hello, everyone. I don't know how many is watching. We have a few minutes left to take questions. I'm looking at the how's it called, swap card thing. I don't see many questions. Maybe what we can say after this presentation is, I mean, if you're using this kind of solution or if using different solutions, from our experience and practice, what's very important, even if you use MPC or TSS, if you have this kind of distributed, decentralized setup, is still very important to make backups and to have BCP, DRP plans, because you will have some key to protect, and it might still happen that some of these devices go offline or that you lose access to these devices. So you always need to have backups whether you use TSS or not. It's not a trick to avoid making backups and having a proper recovery system. I see some not questions, comments. Yeah, and also what's maybe obvious but that we want to say, if you follow the news recently, there's been some 51% attacks on Ethereum Classic and ETC. So of course you can throw crypto at the, let's say, at your wallet, put some TSS MPC, you name it. But if you have an attack on the blockchain behind, if the blockchain sucks, then no amount of crypto in your wallet will save you. So you also want to be careful, with which asset, with which cryptocurrency you work. And also, if you have some privacy, if you have some currency that is not anonymous, such as Bitcoin, then MPC will not protect you against it. That's quite obvious. But where can we find a link to the paper? Good question. It should appear on the Black Hat website in the next hours or maybe tomorrow. I mean, usually they'll usually put it online the day after or 2 hours later. We just put the slides online. There's the link on my Twitter and in the Swapcard interface. So you can look for it. And then again, if you have questions, everything, feel free to contact us. We'll be happy to talk about it. You see, we like talking about crypto, about blockchain. Can't stop us. So yeah, so we have the paper online. We have documentation on GitHub, as you can see on the chat. So yeah, hope it was useful to you, and hope to see you online or in person next year at Black Hat. Time left. Looking for questions. Oh, have you seen any of these attacks in the wild? I have not. I don't know if Omer has a different perspective. Supposing the privacy can be avoided by creating storing keys in HSMs. Yeah, if you put keys in HSMs, you need to use data and you need to use hardware, some hardware HSMs, which can get you quite a high level of security. And you can also combine thresholds, threshold signatures with HSMs. So again, it depends on your use case or on your model, on what you need, also in terms of hot wallet, cold wallet. All the broken code open source. I think most of it, we did not do reverse engineering from binaries to look at this code. Any cryptocurrency more vulnerable? Not really. So in this case, these attacks, they are specific to the wallet technology. They are not directly tied to any specific blockchain. They are related to one signing scheme, so they might apply to ECDSA, the 25519. So more generally about cryptocurrency security, no specific comments. It's very hard to tell.
I want to say that about the question of how many cryptographers are involved in development of such libraries. So it's really good question, because to find cryptographers, applied cryptographers, it's they are rare. So usually the structure of such companies is that you have one cryptographer that actually is doing the work, and then like one or two that is doing formal auditing. And you probably also have your code reviewed by some other, like the theoretical cryptographer. What? And so it mostly comes down to battle testing your code. So this is where I think most of this stuff gets exposed.
Someone asked if we've looked at another custody, cloud-based wallet solution that I may not name. We have not. I don't know if it's open source. And I don't know much about it.
Closed source. Yeah.
Nothing to say. Such attacks. Well, mitigation, good secure SDLC process, maybe do some audits and hire good people and test your code, understand what your and hope for the best.